Yeah, everything is ready. Okay.
Yeah. Okay, so let's get started. So welcome to the second physics club of the semester. So today we're extremely happy to have Professor Shu-Heng Shao from the Yang Institute for Theoretical Physics at Stony Brook University. So before starting as a faculty there, Shu-Heng got his PhD from Harvard University and was then a postdoctoral fellow at the Institute for Advanced Study in Princeton. Shu-Heng has made contributions to a wide variety of different theoretical topics, ranging from high energy particle physics to condensed matter physics to quantum gravity. And so in the last couple of years, he's kind of focused his attention on better understanding the nature of symmetry in these systems, which is what he'll tell us about today. So take it away, Shu-Heng.
All right, thank you very much, Ian, for the invitation and for this nice introduction. Let's see if everyone can hear me well. All right. All right, thank you very much. It's a great pleasure to be here at Yale. So today, as Ian already introduced, I will talk about various generalizations of global symmetries. The symmetry has proven from time and again to be of fundamental importance in describing our nature. In recent years, there has been a revolution in our understanding of symmetries, especially about global symmetries, which I will say, which is the main topic of this talk. And these generalized global symmetries are some of the few universally applicable tools in analyzing genuinely strongly coupled quantum systems. These techniques are not restricted to supersymmetric models nor integrable systems, and they have applications in different disciplines. So before I go to the main part of the talk, let me just give you some flavors about what kind of constraints, what kind of results we can get from the generalized symmetries. These symmetries lead to several surprising consequences, such as new constraints on renormalization group flows, new implications for phase diagram of gauge theories, a new organizing principle for quantum phases of matter in condensed matter physics, a new interpretation of various real-world physics, such as the pion decay. And it has really arisen from an active collaboration between high-energy physicists and condensed matter physicists, also quantum information theorists, experts working on quantum gravity, and also mathematicians. So I really think it's an exciting time to be working on this subject. We get different ideas from different communities. So before we start, we should really ask the central question that we would like to address throughout this whole research program is, what is symmetry? And I would like to start with a brief discussion between global symmetry versus a gauge symmetry. Gauge symmetry, or sometimes also known as the local symmetry, is extremely powerful. It's useful in making the theory manifestly Lorentz invariant, unitary, and local. It is useful because it's the language of the particle physics. Standard model has the SU3 times SU2 times U1 gauge group. In general relativity for gravity, diffeomorphism is also a gauge symmetry. However, if you look at the Hilbert space of your quantum system in compact space, because of the Gauss law, gauge symmetry will act trivially on all the states. Every state is gauge invariant. And therefore, gauge symmetry, in a sense, is not really a symmetry because it acts trivially on all your states in the Hilbert space. It is sometimes called a redundancy of your system. To make this point even sharper, there could be quantum system where there are more than one description. In one description, there could be a gauge symmetry, but in another, there isn't. A very cute baby example of this is to consider a free photon in 2+1 dimensions in the continuum. So this is just free Maxwell gauge theory in 2+1D. Now, in our real world, we know when the photon is propagating in this direction, then there are two possible polarization. It can polarize in this transverse direction or that transverse direction. Now, imagine your space is a two-dimensional plane, and your photon is propagating in this direction, then it has no other choice but to polarize in the unique transverse direction. So that is to say, a photon, a free photon in 2+1D has only 1 degree of freedom. And that's the same number of degrees of freedom as a free scalar field. And in fact, there's an exact duality between these two continuum quantum field theory. On the one side, you have the free photon, and on the other side, you have a free scalar field phi. The more precise duality dictionary between the two is that the magnetic and electric fields are related to the derivative of the scalar fields in this way. I'm suppressing various coefficients. That's not important for my talk. But you see, across this duality, they really describe the same quantum system, but in just two different languages, using two different Lagrangians. On one side, you have a gauge symmetry. It's the ordinary U1 gauge symmetry of a free Maxwell theory, just in 2+1D. But on the other side, this is a free scalar. There's no gauge symmetry. So this simple example shows that it could be that you have a gauge symmetry in one description, but not in another. And gauge symmetry is not supposed to be a fundamental invariance of your quantum systems. This is extremely common in condensed matter physics. In fact, the example I gave is a baby version of the more general particle vortex duality. And in particle vortex duality, it is common that you have gauge symmetry on one side of the duality, but not the other. In contrast, global symmetries acts non-trivially on the Hilbert space. It is an intrinsic property of the quantum system that should be matched under duality. Global symmetries can have anomalies, which is an important concept, and as famously demonstrated by 't Hooft in the 80s, anomalies can lead to non-trivial constraints on the renormalization group flows. Since global symmetry is an intrinsic property of the quantum system, it is therefore important to be able to characterize the global symmetries of a quantum system completely invariantly and independent of the Lagrangian description that you use to describe your underlying quantum system. And I should emphasize that throughout the talk, the adjective global will be used in the following way. It doesn't necessarily mean that the symmetry acts globally on the whole space, even though historically that's where the adjective comes from. But throughout the talk and also in a big community in the field these days, the adjective global is used to contrast with the adjective gauge. Gauge symmetry is something that acts trivially on the Hilbert space, and global symmetry is a true symmetry that acts on your Hilbert space and transform your operators. Okay, but so we have a brief discussion between on contrasting gauge symmetry versus global symmetry. But what is a global symmetry? Many different people have different opinions, different definitions of global symmetry. So let's go through a few of them. Most conventionally, we would say global symmetry is the transformation of the fields that leave the Lagrangian invariant. You have a Lagrangian that depends on phi or derivative of phi, so on and so on. And you do an infinitesimal transformation. If it gives back the same Lagrangian, that will be a global symmetry. If you are more advanced, you might say that, oh, the Lagrangian doesn't have to be invariant. Maybe only the action has to be invariant. If you are even more advanced, you might say that, oh, the action doesn't even have to be invariant. Maybe just e to the is has to be invariant. But what if the quantum system doesn't have a Lagrangian? Then this definition doesn't quite apply. And moreover, there could be quantum system with more than one Lagrangian, just like the free photon example. In some cases, the symmetry might not even act in a manifest way on the fundamental fields of your Lagrangian. So this clearly is not going to be a satisfactory definition of what we mean by global symmetries. The second attempt is that, okay, maybe let's work in a more Hamiltonian picture. A global symmetry is just some unitary operator U that commutes with my Hamiltonian. But Einstein would then beg to differ, because what's so special about the time direction? What's so special about our Hamiltonian? What if I make a boost to change my time direction to be any other time-like direction? Then how do we invariantly understand the definition of a global symmetry? A third point of view is that I don't need a Lagrangian. I don't really want to talk about Hamiltonian either. But whenever I have some operator, some conservation equation, some operator satisfying some first order differential equation, just like this one, then I will call that a global symmetry. Well, that works perfectly well for continuous symmetry, like a U1 symmetry, some particle number conservation symmetry, where in that case, rho will be the particle density. But what if the symmetry is discrete? For discrete symmetry, there's no conservation equation. What if the symmetry we're talking about is CP or time reversal or some charge conjugation? How do we understand? Finally, do symmetries have to be unitary or anti-unitary? Well, Wigner say yes, but really? In later part of the talk, we will see some examples that you might be tempted to call them symmetries as well, but they are not unitary. Now, I'm not going to give you a definitive and universal answer to any of these questions in this talk. I really think this is an ongoing conversation, and I really got stimulated by talking to different people with different notions of global symmetries. But I will try my best to give a somewhat coherent picture throughout the talk that put many developments in this subject into a single framework. So let's move on to the details. So I will talk about 3 generalizations of global symmetries in this talk. The first one is known as the higher form global symmetry. There are many examples of higher form symmetries, such as the center symmetry in gauge theory, and also abelian anyons in the low energy limit of certain condensed matter system can also be thought of as a higher form symmetry. The second example will be called the subsystem symmetry. This is a symmetry that has played a very important role in the development of various exotic lattice models that has been actively studied in condensed matter physics and quantum information theory, especially in the field of fractons. And finally, I will talk about a very exotic type of symmetry known as the non-invertible symmetry. Roughly speaking, it's a symmetry that cannot be undone. You might think it's totally weird. Maybe you have to cook up some very fine-tuned, high-dimensional, supersymmetric models to see them. But actually, it turns out that the non-invertible symmetries exist quite ubiquitously in many familiar quantum systems, starting from our favorite Ising model, non-abelian anyons, and even our real-world QED and QCD. And I will briefly mention how the non-invertible symmetry can be used to explain the neutral pion decay in the real world at the end of this talk. And tomorrow I will give another seminar here at Yale, and I will say much more about this particular topic. So that's the plan of the talk. And before we talk about generalized symmetry, let's say a little bit more about the ordinary symmetry. And this is probably one of the first examples of global symmetries in quantum field theory that we learn in any quantum field theory courses. So let me start with the quantum field theory with a conserved Noether current. And this is a relativistic quantum field theory. My Noether current is a vector or one form, depending on how you want to look at it. It obeys this first order conservation equation. Starting from the Noether current, you can build a U1 symmetry operator. Now, what is this operator that generates the U1 symmetry? You take the time component of the current, you integrate it over the whole space, and that gives you the conserved charge. And you further exponentiate it with some angle theta. The theta tells you what's the rotation angle you perform on your quantum state. And you get an operator U theta. It's supported on the whole space because I integrate over d3x. And it's an operator at a fixed time acting on the state in your Hilbert space. Now, thanks to the conservation equation, it's a one-line algebra to show that the charge and also the symmetry operator U is conserved. And by conserve, I mean if you hit it with a time derivative, you get 0. Because you hit the time derivative into the integrand, and then you apply the conservation equation. The integrand becomes a total derivative, you get 0. Quantum mechanically, that means this U operator commutes with the Hamiltonian. That's a symmetry we are all familiar with. For relativistic systems in Euclidean signature, the time direction is completely on the same footing as any other direction. So there's no particular reason to single out the time component here and integrate it over the whole space at a given time. You can be more creative. You can choose the one form and to integrate it over any three-dimensional manifold in your four-dimensional Euclidean space-time. So this is a simple generalization of the unitary operator U on the previous slide to something more general. Now this U, I still call it U, but it depends on the choice of the manifold. This M is a three-manifold in your space-time. The three-manifold could be the whole space at a given time, just like in the previous slide, or it could extend in the time direction. In that case, when M extends in the time direction, it's not an operator because it exists in every time. Rather, it modifies your Hamiltonian. It modifies the quantization of your system, give you a twisted Hilbert space, and that's a defect. So really from the conservation equation, J, for J, you can either get an operator that acts on the state of your Hilbert space, or you can get some more general defects that extend in the time direction and modify your quantization. You can think about it as twisting the boundary condition of your field. Maybe originally you have a scalar field that's completely periodic as you go around in space, but now with the insertion of this defect, it might flip a sign as you go around in space. Previously, we learned that the operator, the conserved operator, is conserved, meaning that if you hit the time derivative, it vanishes. But in relativistic system, there's nothing special about the time direction. You can also hit it with a spatial direction, it should also vanish. And more generally, what we learn from the conservation equation is that this U of M only depends on the choice of the manifold topologically. So you can have your M being some codimension 1 manifold in your spacetime, and you deform it a little bit, it's not going to affect any observable you are trying to compute. So the upshot of this discussion is that in a relativistic system, the ordinary notion of conservation, namely independence of time, is upgraded to the notion of topological property. It means that you can define a more general U of N that you can insert in any correlation function, and the observable will only depend on the choice of your M topologically. So this makes a connection between symmetry and topology that will play an important role in the rest of the talk. So let me just summarize what I just said in the previous slide using this column. Let's start with the ordinary symmetry. It's supported in a codimension 1 manifold in space-time. That sounds like a fancy statement, but in the special case when it's an operator spanning over the whole space at a given time, that manifold M is just your whole space. And as we explained before, for ordinary symmetry, especially for the case of a continuous symmetry, the conservation, the notion of conservation is upgraded to the fact that this U is topological. Finally, for an ordinary symmetry, it obeys the group-like fusion rule. If I have this U with theta labeled by theta 1, and I bring another U parallelly to it with theta 2, the exponential, when the exponential multiply, their exponents just add up. And I get another U whose theta is theta 1 plus theta 2. That's just the U1 group multiplication law. For ordinary symmetry, more generally, the fusion rule will obey the group multiplication law. Now, starting with setup, I'm going to generalize the ordinary global symmetries by modifying some of these conditions. So let's take a look at our first generalization. The first one will be higher form symmetry. For higher form symmetry, its support in space-time will be of higher codimension. So you might not span over the whole space. You might only span, say, only a line in your whole space at a given time. It's still topological. It still obeys the group multiplication law. The second generalization, which is somewhat similar to the higher form symmetry, is called the subsystem symmetry. Its codimension, similar to the higher form symmetry, is also greater than 1. For example, if your system is a two-dimensional lattice, maybe this symmetry only rotates your rotors along one column of your lattice, but not elsewhere. That's why it's called a subsystem symmetry. The important difference compared to the higher form symmetry case is that it's not completely topological. It is conserved in time, but the charge supported on this column might generally be an independent operator quantum mechanically to another charge at the nearby column. And already at this point, you recognize that subsystem symmetry does not respect the Lorentz symmetry. So it does not exist in any Lorentz invariant quantum field theory, but it has made a very important. It has played a very important role in many non-Lorentz invariant lattice systems. And finally, it still obeys the group multiplication law. For non-invertible symmetry, its codimension is completely general. Mostly in this talk, I will talk about the case when the codimension is 1. Namely, you can think about it as an operator at a fixed time covering the whole space. It is topological, so it does exist in relativistic system. However, it's not implemented by a unitary operator. D times D dagger is now 1, and generally you get many more stuff on the right-hand side. And we'll see where that comes about. And I should really say that these 3 generalizations are really just a small subset of all possible generalizations. You can take these 3 columns, take any linear combination of them, and there exists realization of this even more generalized situations. But in this talk, I will just focus on these 3. Okay, I'm going to move on to the first generalization, the higher form symmetry. So we are now in this column. The higher form symmetry, I think, was articulated in this paper back in 2014. For ordinary zero-point symmetry, well, for ordinary global symmetry in this terminology will be called zero-point symmetry. And what does the 0 stand for? It means that it acts on point operator or local operators, if you wish. So imagine you have some complex scalar field phi, and a global symmetry rotated by a constant phase. A one-form global symmetry acts in the following way. So in gauge theory, a one-form global symmetry can act on the gauge field by shifting it by a one-form. But this one-form cannot be an arbitrary one-form. If it were an arbitrary one-form, it generally would not leave the Lagrangian invariant. Rather, it is a one-form that is closed. It's a one-form which itself comes with a trivial electric and magnetic field. At this point, you might think, oh, well, it acts on a local field as well. It's the gauge field. So why do we want to call it a one-form symmetry? It doesn't seem to be that dramatically different compared to the ordinary case. Well, the difference is that the gauge field is not really a good local operator. It's not gauge invariant. It transforms under the gauge transformation. The real gauge invariant observables in a gauge theory are the Wilson lines. So you integrate A along some closed curve in your space-time. And this one-form global symmetry acts on this gauge invariant one-dimensional object. And the fact that it acts on one-dimensional gauge invariant objects is the reason why it's called a one-form symmetry. And more generally, a Q-form global symmetry will act on a Q-dimensional extended gauge invariant object. The charge for the one-form symmetry in a free Maxwell theory is nothing but the electric flux surface operator. So you take your electric flux, integrate it over some surface. Notice that a surface in our 3+1D real world will be codimension 2 in space-time. So that's one codimension higher than the ordinary symmetry case. And that's another reason why it's called a higher form symmetry. More generally, in non-abelian gauge theory without any quarks, there's a ZN center symmetry, which acts on the Wilson line. And that's also one example of the one-form symmetry. Well, at this point, you should feel like, duh, this is just center symmetry. This is just the electric flux. Why are we attaching fancy names to some existing concepts? One advantage of grouping this existing old concepts into a bigger coherent picture is that it allows you to apply some ordinary notions for ordinary symmetries to this more generalized setup. For example, ordinary global symmetry can have anomalies. And by anomalies here, I mean obstruction to gauging the very global symmetry. And such an obstruction, as famously discussed by 't Hooft, will lead to matching condition along the RG flow. So in the ultraviolet, you can try to compute this obstruction to gauging the symmetry, and that obstruction should be robust and preserved along the renormalization group flows. A non-trivial anomaly would imply that the low energy phase cannot be a trivially gap phase with a non-degenerate ground state and no topological degrees of freedom. And one very nice application of the higher form symmetry is that it was realized in this paper in 2017 that just take the 3+1D SU2 Young-Mills theory, literally the same Young-Mills theory that Young and Mills studied back in the days. But the only new twist you threw into it again is that you add a theta term. And you carefully tune the theta term to be pi. So you're halfway through this theta angle circle. This paper realized that the SU2 pure Young-Mills theory at theta equals to pi has a mixed anomaly between the CP symmetry and its Z2 one-form center symmetry. And this anomaly implies that the low energy phase of the SU2 Young-Mills theory cannot be a trivially gap phase with non-degenerate ground state. This is an analytic constraint you get just by analyzing the anomaly of this generalized global symmetry. This is to be contrasted with the general consensus that at theta equals to 0, the low energy phase should be trivially gap with a finite mass gap. Of course, that's not proven yet. If you can prove it, you'll get a $1 million prize from the Clay Institute. So that's one application. There's a second application that's more in the condensed matter physics area. So we all know the Landau paradigm, which states that phases of matter should be classified by how they represent the symmetries. This works very well for a lot of the standard phase transitions, such as the Ising transition, which you can understand it as whether the Z2 global symmetry is broken or not. But there are many exceptions to this vanilla version of the Landau paradigm. For example, there are topological orders in 2+1 dimensions. These are topological phases of matter that seemingly have no symmetry, but they are distinct with a trivial matrix product state. In the low energy, topological orders are described by Chern-Simons gauge theories in 2+1D. And the anyons of this topological order, in the low energy, they become the Wilson lines of the Chern-Simons gauge theory. And they generate the one-form global symmetries. And the one-form global symmetries in those topological order can be understood as being spontaneously broken. So by including the one-form symmetries into the notion of global symmetry, now you can understand the topological order as a spontaneous symmetry breaking phase of a one-form global symmetry. And that extends the traditional Landau paradigm to these more exotic phases of matter. Okay, that's all I want to say about higher form symmetry. Next, I would like to move on to another kind of symmetry that has played a prominent role in condensed matter physics. That's the subsystem symmetry. So we are now in this column. So similar to the higher form symmetry, is supported on some higher codimension manifold, but it's not completely topological this time. So back in the free Maxwell theory case, we talk about the one-form symmetry that's implemented by electric flux. Now, if you have a point source charge, say an electron here, and you encircle that electron by a sphere and measure the electric flux, you get the same answer, no matter if you encircle it by a sphere or a box. And that follows from the Gauss law. And that tells you that the electric flux operator is topological. You can deform it arbitrarily as long as you don't pass any charge sources. But for subsystem symmetry, we'll see that something is going to be different. So in recent years, there are many interesting lattice models, especially the fractal models that exhibit subsystem symmetries. Subsystem symmetry charges that are supported on certain hierarchical dimension loci in space. So unlike the electric flux, where you can draw an arbitrary shape in space, surface in space-time to measure the charge, for subsystem symmetry charge, they are more restricted. For example, there are examples where your space is a two-dimensional lattice, and you only have a conserved charge along the straight lines that are along either the x direction or the y direction on your lattice. You cannot draw an arbitrary curved line that would not lead to a conserved quantity. And moreover, the conserved charges are generally independent as you vary the coordinates. So the charge here at x equals to 0 is generally an independent charge as the charge at x equals to 1, for example. So they depend not only on the topology of the manifolds, but on more details on the choice of the locus. And generally, the number of subsystem symmetry charges will depend on the number of lattice points. Say that at site number 1, you get a charge, but at site number 2, you get a different charge. And this seems somewhat bizarre from a continuum point of view. As you take the continuum limit, you take the number of lattice sites to infinity. And naively, you will get infinitely many conserved charges in the low energy limit of such exotic systems. And that leads to several surprising consequences go under the name of UV-IR mixing. And we'll see examples of that. But roughly speaking, by UV-IR mixing, I mean there are certain IR observables, such as the ground state degeneracies, that will be sensitive to the microscopic details, such as how many number of lattice sites you have in your lattice model. And fractals are a large class of lattice model that exhibits the subsystem symmetry. So fractals originally, one of the most important papers on fractals was about robust quantum memory. But since then, it has drawn a lot of attention in the condensed matter literature, trying to understand how this novel topological phases of matter will fit into a more conventional quantum field theory framework. So I'm not going to tell you much details about fractals, but roughly speaking, there are just some gap lattice spin models that mostly study in 3+1D. So your space is a three-dimensional lattice, and you can take it to be a cubic lattice, like the one I try to draw here. And on every length, for example, you just have some Z2 spin. Could be spin up or spin down. Not so different from the Ising model up to this point. But the important difference is that the local interaction between those spins are designed in a particular way. For example, in one of the simplest fractal model, known as the X-cube model, their spins interact through around the cube in this way, in one of the turns. And in another kind of turns, the four spins interact in this way. The details don't matter. The important thing is that the interaction is completely local, and you just have some spin degrees of freedom in the UV. But as you go to the low energy, people realize that this lattice model actually exhibits a lot of bizarre peculiarity. One of the peculiarity is that the ground state degeneracy of this lattice model is extremely large. First of all, the model is gap. As you go to the low energy, there are a bunch of ground states, and then there's an energy gap. But the number of ground states will scale will grow sub-extensively in the linear size of the system. More specifically, in this model called the X-cube model, if you put it on L by L by L cubic lattice, then the number of ground states goes like 2 to the 6L minus 3. It grows exponentially in L. As you take the continuum limit, L goes to infinity, and you seemingly get infinite ground state degeneracy. So it doesn't seem to fit into any conventional quantum field theory description. How do we understand this infinite ground state degeneracy from a continuum point of view? And this has been an active research subject, both in condensed matter physics and in high energy physics. You might think this ground state degeneracy is an accident. I can take just a bunch of free spins, trivial Hamiltonian. That system has an extensive ground state degeneracy. But that's not interesting at all, because once you throw in any local perturbation, that would lift the ground state degeneracy. However, people can rigorously show that in the fractal model, this large ground state degeneracy that grows exponentially in the linear size of the system is completely robust. There's no local perturbation that you can add to lift the ground state degeneracy. So it's really not an accident.
This ground state is a classical ground state defined by the classical energy, or ground state of the quantum Hamiltonian connected.
It's a ground state of a quantum Hamiltonian. So I can be a little bit more specific. Here I drew, so on every link, you have a two-dimensional qubit. And you can have the sigma x and sigma z Pauli matrices acting on the qubit. And in the quantum Hamiltonian, you have two kinds of terms. You have the product of the sigma x's multiplied in this particular way. That's one kind of term. In the other terms, you have the sigma z's multiplied in this particular way. There are actually also classical analog, but I'm not going to discuss them here. In the technical term, these are some stabilizer code. Any other question? Okay, so that's the peculiarity of ground state. You have a large ground state degeneracy that just continue growing as you increase the number of lattice sites. And in addition to the ground states, their excited states are also funny. In this systems, there could be point-like excitation. By that, I mean there could be an excited state where its energy is completely localized at a point in your space. And that point excitation cannot be moved arbitrarily. Its motion is restricted. It could be that one of them cannot move, but a pair of them carrying the opposite charge can move collectively. So this is known as the restricted mobility of the fractal system. So one of the big question in this subject is how do we understand these peculiarities from a symmetry point of view, and how do they fit it into a continuum field theory picture? The way so in the past we have developed a generalized global symmetry framework to give a universal explanation for these two particular peculiarities that we just explained. So ordinarily, when we talk about global symmetry, it's a global symmetry, as I said, at a fixed time, acting on your Hilbert space. So it acts on the state, it acts on the operators, but it doesn't act on the defects. You can, in your system, you can insert the impurity, and that impurity will stay there until the end of the time, and then modify your Hamiltonian. How do we think about symmetries that acts on the defects? So with this distinguish two kinds of symmetries. One of them is called a space-like symmetry, and the other is called a time-like symmetry. Space-like symmetries are those symmetries that you are more familiar with. They act on operators that are space-like in space-time. Whereas for time-like symmetries, they act on defects that extend in the time direction. It turns out that in fractal systems, the ground state degeneracy can be understood in terms of the space-like subsystem symmetries and their anomalies. Whereas the restricted mobility for the excited state, once you go to the low energy, those excitations become defects. And their restricted motions are interpreted as certain selection rules on the defect amplitudes. And these are explained by the time-like subsystem symmetries that act on the defects. There could be even more exotic fractal model, so I just want to give you a flavor of that goes beyond the scope of subsystem symmetry. So previously, we talked about conserved charges that are supported along a line in your space. But it could be that there are conserved charges that just kind of spread out sporadically on your whole lattice. It's not along a line in space, but it also doesn't cover the whole space. It could be that it covers some fractal shape geometry on your lattice. So one of the most celebrated fractal models is called the Ha-code, and it does exhibit such fractal structure. And recently, there's also a very nice paper by Meng Chen and collaborator who used transition theory and stacked them together to get some exotic global symmetry. And recently, there has been some papers about how to define fractons on a more generalized lattice. So previously, we talked about fractons on a cubic lattice. But if you take your more familiar Ising model, we know how to define on a completely general lattice. But for fractons, generally, we don't know how to do that. But there are certain types of model where you could do that. And it's somewhat analogous trying to define a quantum field theory on a general curve manifold. You first learn quantum field theory in Minkowski space, but then you slowly start to learn how to put it on a more general manifold, like in de Sitter space or our FRW universe. So in this references, a new gap ZN fracton or linear models that has been developed, and it can be placed on a general graph lattice. And the way that the ground state degeneracy depends on the lattice will be even more exotic. So for example, you can take the spatial lattice to be an L by L cubic lattice, and then the log of the ground state degeneracy goes like this. So the horizontal axis is the number of lattice sites. The vertical axis is the log of the ground state degeneracy. And you can see that it jumps around. The important feature is that there's actually a sequence of L going to infinity such that the ground state degeneracy lies on this line. So there's this point, there's that point, so on and so on. So it means that there's a sequence of L going to infinity such that your ground state degeneracy grows like e to the L. So that's the feature that we advocated earlier in the simpler model of fractal, the XQ model. But in this more exotic model, and also in Haas code, the ground state degeneracy depends on the number theoretic property of the number of lattice sites. If L is, for example, if L is even or odd, you get a completely qualitative different behavior. And in fact, in this model, not only that there are sequences of L going to infinity in such a way that the ground state degeneracy grows exponentially, there are also sequences of L such that the ground state degeneracy stay finite. So it's even more puzzling how one would explain this from a continuum point of view. That's all I want to say about fractons and subsystem symmetries and some even more weirder symmetries. And now I want to move on to the third generalization, the non-invertible symmetry. So we are now in this column. We are back to symmetries that are generated by topological operators. So we are now back in the relativistic world. Okay, so I want to start with a very simple example of non-invertible symmetry, because the name sounds a little bit intimidating, but it's actually something that we have all seen before, but we just didn't put it into that language. And later on, I will gradually talk about more advanced examples. So let's consider an ordinary global symmetry, a rotation symmetry. So you start with a cat state, and you apply a unitary rotation operator u theta on this cat state. You just rotate it by an angle theta. This is an ordinary invertible symmetry in the sense that if you want to rotate it back, just apply u minus theta, and you get back the original cat state. Now, this is true both classically and quantum mechanically. But quantum mechanically, there's something new you can do. In quantum mechanics, we can take superposition of states. Schrödinger's cat can be both alive and dead. So in particular, let's consider the operators u theta plus u minus theta. And I'll give it a new name, it's d. Now the way d's add on the cat state will give you a superposition of two cat. Now it's not an invertible symmetry, it's not an invertible operator. U theta commutes with the Hamiltonian, u minus theta commutes with the Hamiltonian, and so does d. But d is definitely not invertible. If you continue acting d on this cat, you just get even more and more cats. But you will not make a big deal out of this because you know d is made out of unitaries. So why bother studying d? I'm just going to study my u theta. And if needed, I'll take combination of those. And we do that all the time, right? If you have a Z2 charge conjugation symmetry, we talk about the Z2 operator, let's say u. You also talk about the projection operator, 1 plus u, maybe divided by 2 if you want to. But when you run into the projection operator, you don't get excited and tell all your friends that you find a non-invertible symmetry. The novelty is that in some quantum system, it could be that the U theta itself doesn't exist. It could be that U theta is not a good operator. This could, for example, arise from a discrete gauge symmetry. Maybe there's a gauge symmetry projecting out U theta itself, but it keeps the combination U theta plus U minus theta. In those cases, you have no choice but to work with D, but not the individual U, because the U is projected out. And in those cases, you have a conserved operator D, which in relativistic system will be more generally topological, but it's not unitary. It's not invertible. It's a symmetry that cannot be undone. And that's the first example of non-invertible symmetry. But I should really emphasize that not all non-invertible symmetries are of this kind. There are even more bizarre ones. But this is an easy example. But why should we think about these topological operators that are not unitary as symmetry? Yeah.
So what happened to Wigner's claim that every symmetry?
Excellent. Yeah, excellent. So you can look up with the Wikipedia page for Wigner theorem. What Wigner showed is that every symmetry transformation is implemented by a unitary or anti-unitary operator in quantum mechanics. But then one should ask, what did Wigner mean when he said symmetry transformation? In his definition, he requires that the symmetry transformation preserve the norm of the state. But that's a condition that I'm going to relax in this discussion. I'm going to discuss operators that commute with the Hamiltonian. In relativistic quantum field theory, it commutes with the stress energy tensor, but it doesn't preserve the norm of the state. In fact, in some cases, it might even have 0 eigenvalue in certain sector of the Hilbert space.
Is the norm of the state or the norm of the inner product of the state?
Yeah, more generally, the inner product of the state, maybe not just the norm. But that's a condition I'm going to relax. And you can justifiably argue with me that why should I call it a symmetry? Symmetry should be invertible. Why do we want to include these more general topological operators that just pull out of my hat? Why should we give it a prestigious name, symmetry? And I think it's an ongoing conversation, but I'm going to give you a few arguments why it is useful.
Could we just say that a non-invertible symmetries mean it's an algebra, not a group?
That's an excellent question. The proper language is actually a category. It's not just an algebra. It has a lot more structure than just an algebra. But I will avoid all of those mathematical framework in my talk, but I would definitely love to discuss more about that. There's a very rich mathematical structure behind. In some cases, the mathematicians have already developed the framework for us. In some other cases, it's wide open. And there has been a very rapid development in non-invertible symmetry in the past year. And mathematicians are also interested in this. And they have recently come up with some new math formulas and to incorporate these new symmetries. But the right word should be category. Any other question before I go into the justification? Okay, so now I would like to convince you why they should be thought of as symmetries. First of all, it leads to new conservation laws and selection rules. So these are not just putting new names to some old ideas. They actually have new consequences that are overlooked before, that are unexplained before. And already in 1+1 deconformal field theory, there are many examples of RG flows that were not previously explained by conventional symmetry. They can only be explained by non-invertible symmetries. Second of all, some of the non-invertible symmetries can be gauged, just like ordinary symmetries. There's a generalized gauging procedure. Third of all, for some other non-invertible symmetries that cannot be gauged, namely when there's an obstruction to gauging them, there's a generalized anomaly. And then there's a generalized to Hoof anomaly matching condition that leads to non-trivial constraints on the RG flow. In some cases, it leads to analytic obstruction to a trivially confining phase in gauge theory. And fourth of all, I'm going to throw in some quantum gravity elements. There are various conjectures in quantum gravity that are believed to be true and proven to different extent. For example, it was argued that in quantum gravity, there shouldn't be any global symmetry. Quantum gravity is supposed to be featureless. Black holes are not supposed to have hair. But that's just about the conventional global symmetry. What about non-invertible global symmetry? What about all this generalized global symmetry? It has been recently argued that quantum gravity should also have no non-invertible symmetries. And by including the non-invertible symmetry into this big family of global symmetry, you can actually consolidate different conjectures in quantum gravity. Once you make this inclusion, different conjectures now become equivalent, and you can just try hard to prove one conjecture and the other will follow. So that's another argument from quantum gravity that you should really include these new symmetries as part of the family. In recent years, there has been a very rapid development on non-invertible symmetries. So back in 2017 or 18, people were working on it mostly in 1+1D. And already there are several beautiful examples, like already in Ising models, both in the continuum critical field theory or also in the statistical formulation of the lattice model, and also in the quantum spin chain, there are non-invertible symmetry. In that particular case, the Cramer's one-near duality line defect. But it exists more universally in almost every 1+1D rational conformal field theory. I should say that I think I only know a handful of rational conformal field theory that doesn't come with a non-invertible symmetry. And from November last year, there has been a really explosion of activities of the study for non-invertible symmetries in higher space-time dimension, in particular, our space-time dimensions. And as I said, they are not implemented by unitary operator, and it can also not be expressed in terms of sums of unitaries. So they're really genuinely non-invertible. And just this May, we found that actually there are non-invertible symmetries in the real world QED and QCD. And I will talk about the details about those symmetries in my talk tomorrow. And the other point I want to make is that since last November, there are not only activities in the high energy physics and condensed matter physics, but there are also mathematicians actively working on it. So just in a matter of months, mathematicians have come up with a new categorical framework to incorporate this new generalized global symmetries into a rigorous setup of axiomatic quantum field theory. And I personally find this very exciting because it doesn't happen every day for me, at least, that a mathematician will pick up a physics idea in a matter of months. Yeah, there's a question.
Yeah, perhaps I'm missing something basic here.
Yeah.
How is the Cramer's one-air duality non-invertible? Like that's just lattice to its dual lattice, right?
So yeah, I didn't get didn't get a chance to explain this, and I won't have the time to explain. But I would love to talk to you more about this. But let me just say in the simplest way. Let me just say in the simplest way. I can either do it on the lattice, or I can try to say in the continuum field theory point of view. So let me start with my comfort zone, namely the continuum field theory, the Ising conformal field theory. Okay, in Ising conformal field theory, there is a Z2 global symmetry. It's the Z2 global symmetry that comes from the spin flip in your microscopic lattice model. And it flips the spin operator. It flips the sign of the spin operator, your older operator. Sigma goes to minus sigma. It leaves all the other operators invariant. But that's it. That's the only Z2 global symmetries you have. However, in quantum field theory, you are usually told that the Ising conformal field theory is the same as a free massless Majorana fermion. That's the 1+1D bosonization / fermionization. A massless Majorana fermion has two Z2 global symmetries. You can flip the sign of the left moving Majorana fermion or the sign of the right moving Majorana fermion.
Oh.
So you have Z2 cross Z2 on the one hand, but you have only a Z2 on the other hand. How can they be the same quantum field theory? So it was a lie that the two quantum field theory are the same. In fact, they cannot be the same from the get-go because an Ising conformal field theory is a bosonic conformal field theory you can define on any Riemannian manifold without a choice of the spin structure. Whereas the Majorana fermion is a fermionic quantum field theory whose observable would depend on a specific choice of your spin structure. The more precise statement is that there's a bosonization and fermionization map relating the two, which, as you alluded to, is the Jordan-Wigner transformation on the lattice. Now you can ask, when you do bosonization of a free massless Majorana continuum quantum field theory, you start with two Z2 global symmetry. What happens to one of them? Because you only see one in the Ising, and that becomes non-invertible. And what it does in the Ising conformal field theory is that so you can think about this, so it becomes a parameters one-near duality line. And as you bring the order operator past that duality line, it becomes a disorder operator. A disorder operator is attached to a Z2 branch cut. It's not a local operator. Order and disorder are nemesis to each other. They cannot coexist. And the very fact that the duality line takes a order local operator to a non-local disorder operator is the hallmark that it's non-invertible.
Thank you.
Yeah. Any other question? All right. So I'll just have one or two slides about the non-invertible symmetry in nature, but I'll say much more about them in my talk tomorrow. So the story is really just in 3+1D massless QED. Okay. It's really the same QED that Feynman, Schwinger, Dyson study. And there's a chiral symmetry that rotates the Dirac fermion famously. But Adler, Bell, and Jacqueff in 1969 showed that this symmetry is not a true symmetry quantum mechanically. There's an anomaly famously known as the ABJ anomaly. But what was realized in these two papers from May this year is that the classical chiral symmetry is actually not completely broken by the ABJ anomaly. They're resurrected as a non-invertible symmetry. And now they're labeled by the rational numbers. So you take your original classical chiral symmetry, it's labeled by some U1 rotation angle. Only those rotation angles that are rational get cured by something. Now, what is that something that cures the ABJ anomaly of a chiral symmetry? It turns out that the medicine that you need to cure the chiral anomaly is a 2+1D dimensional fractional quantum Hall state. So here I just wrote a formula with no explanation of details, but I'll say much more about it tomorrow. But the upshot is that the fractional quantum Hall state cure the ABJ anomaly and resurrect the rational worth of the chiral symmetry into a non-invertible symmetry. There's an identical story in massless QCD. In fact, that was the motivation why Adler, Bell, and Jacqueff looked into the problem. And if you apply the same construction in QCD, you realize that QCD also have a non-invertible symmetry. And that non-invertible symmetry in the QCD should be matched by the low-energy pion Lagrangian. How do you match it? The only way to match it is to have a pi0FF coupling the pion Lagrangian. And that is the term responsible for the neutral pion decay. So in the maximally offensive way, I can say that neutral pion decay in the real world decays because of the non-invertible symmetry. I should say that I think this is a perfect example of interdisciplinary research program, because there's no way that Adler and Bell and Jacqueff would have figured out the non-invertible symmetry back in '69, because there was no fractional quantum Hall state back in '69. And it's really the idea from the condensed matter physics imported into this high energy physics context that give rise to these novel symmetries. So the history of chiral symmetry in QED looks like as follows. Before '69, everyone thought, yeah, chiral symmetry of massless QED is a symmetry. But after '69, we realized it's not a symmetry, it has the anomaly. But now we realize it's actually a non-invertible symmetry. And furthermore, there could be non-invertible CP symmetry. So usually we say that the theta angle of a gauge theory will break CP or time reversal symmetry. Now, if you are slightly more advanced, you will know that at theta equals to pi, CP is also there. But away from theta equals to 0 and pi, we generally don't think there's a CP symmetry. But in free Maxwell theory, or in the real world massive QED, actually we realized that there is a time reversal symmetry at every rational theta angle. And this is the phase diagram of the free Maxwell theory. I'm not going to explain any details, but it shows where various non-invertible symmetries are, just for the free Maxwell theory, the same theory that Maxwell studied. Or maybe that's a lie because he didn't really study the theta angle. And at a rational theta angle, you don't have an invertible CP or time reversal symmetry. Instead, you have a non-invertible CP symmetry. Okay, I should wrap up my talk. So we have discussed three generalizations of global symmetries. The first one is higher form symmetry. The second is subsystem symmetries. And the third is the non-invertible symmetries. And there are many, many other generalizations. This more general perspective of global symmetry unifies many known phenomena into a coherent framework. Like we saw that we could use the global symmetries to explain some known peculiarity of the fractal models. Also, the inclusion of the higher form symmetries generalized the Landau paradigm to make it work for novel topological phases of matter, such as the topological order for anyons. But it would be disappointing if that's all this generalized global symmetries can achieve. You want to be able to say something new. And indeed, there have been a lot of developments on that. This new symmetry may lead to new dynamical consequences that are otherwise completely obscure. There are new anomalies coming out of this formalism, and you get new constraints on the phase diagram of your theories, on the RG flows of your theory. And I would also like to emphasize that these are really new symmetries in both new quantum field, new quantum system, and old quantum system. The new quantum systems, including fractons. There are new exotic subsystem symmetries, fractal symmetries there. But also in old quantum systems, such as our QED and QCD, there seems to be new symmetries that have not been discussed before. Looking forward, there are several questions we would still like to answer. Of course, the obvious one is what qualifies as a symmetry? Does this family of symmetry just continue to expand? And are there more new global symmetries in our real world? Are they useful? And I personally think these new symmetries, they're perfect for the study of hierarchy problem or naturalness problem. For example, we saw that there are new time reversal symmetries, even at non-zero theta angles. Can we say anything about strong CP? The short answer is no, but I would love to have more to say about it. And in the condensed matter physics setup, how do we organize or even classify different phases of matter using these new symmetries? I think it's a really exciting time to be working on this subject because, as I constantly said, it's really it's really ideas from different communities of people. There are high energy theorists who work on quantum field theory. There are high energy theorists who are interested in quantum gravity. They are interested in swampland problems. And there are also condensed matter physics interested in stabilizer code, fractons, anyons, TQFTs. And finally, there are also mathematicians trying to formulate global symmetries in a rigorous way in the axiomatic quantum field theory approach. And different perspectives bring in new ideas. And I should mention that there are two Simons collaborations, at least two Simons collaborations that are related to this research program. There's an ultra quantum matter collaboration that kind of bring the high energy physicists and the condensed matter physicists together. There's also a newer Simons collaboration on global categorical symmetry. It has category in the title that brings the mathematician and the high energy physicists together. And I just want to advertise two more activities next summer. So next summer, I will be co-organized TASI 2023, and the central thing will be about symmetry. And also there will be an Aspen workshop I'm co-organizing that's trying to bring the more final and formal high energy physicists together to see what all these new techniques developing on the formal side can be applied to interesting final questions. And I'll leave you with this slide. Thank you very much.
Okay, so thank you very much for that exceptionally clear colloquium. Do we have any questions beyond those already during the talk?
Thanks. So you mentioned a little bit in the higher form symmetry about confinement. I was curious, just generally, if you think these higher form symmetries and objects are a good sort of avenue to better understand features of, or even confinement itself in QCD, Yang mills generally.
I think actually the most fundamental question is, what is confinement? And there's oblique confinement. Sometimes there's no clear phase transition from a Higgs space to a confined phase. In a way, higher form symmetry provides the clearest definition of confinement. It might be a little bit too restrictive depending on who you talk to, but the definition of confinement in the context of higher form symmetries is in terms of whether the higher form symmetry is spontaneously broken or not. And that's a completely invariant notion. And that I think that really clarifies all these oblique confinement examples. But I should say that if you want to win the $1 million prize from the Clay Institute, you should really read their description. The description is not about proving confinement, but proving the mass gap. So that's a separate issue. But I think conceptually, actually, higher form symmetry provide the most clear-cut definition of what one could mean by confinement.
Thanks.
Are there any other questions?
So this might be a pedestrian question, but I was wondering, so when you talked about time-like subsystem symmetries, is the idea that you have these defects now, which I would think would generally break the symmetry of the lattice that was there before, and you're like raising it to some different symmetry, or?
Not quite, sorry, I was very brief in that discussion, so it wasn't really clear what I was talking about. So the idea is that you have some defects, say on the lattice, some impurity, if you imagine, and it sits somewhere on your system. It just stay there forever. That by itself is not necessarily a symmetry, it's just a defect, some impurity. Now, the point is that the time-like symmetry is some operator in your algebra of operator that can act on this defect configuration. It assigns a phase to that defect. So there are really two objects here. There's one thing that's charged under the time-like symmetry. There's another thing that implement the symmetry transformation.
Thank you.
Yeah.
Okay. Maybe one more question for Shu-Heng, and then we should wrap it up for time.
Hi, this is a bit of thought for speculation. So it seems that we had some symmetries classically that we thought were lost, and then we were able to reclaim some of it. And to reclaim some of it, we had some new mathematical insights. Maybe I'll just ask if you can speculate, do you think there'll be more of what we think is lost being reclaimed in the future in some fancier form of math, or is there some sort of?
Yeah, I'm writing a paper about it. Yeah, there are certainly more. Yeah, I wouldn't hope that paper is the last one on this subject. Right. So
yeah, but I meant, like, for example, in this case of like the rational parts of being reclaimed, do you think the parts that are not rational are also going to be reclaimed in some sense?
In that particular case,
or in cases like that, maybe there's some even more general mathematical notion that.
There could be, but in the QED case, I don't think anything beyond the rational rotation can be resurrected. The simplest argument is that there's no irrational quantum Hall state. Okay. There are only fractional quantum Hall state. Okay. So you only have the medicine to cure the rational ones.
Okay. Thank you.
Yeah.
Okay, so I think for time, we should wrap things up now, but I'll just advertise again that Shu-Heng will be giving a more technical talk tomorrow afternoon. But let's thank Shu-Heng again for that great colloquium.
Thank you very much.